Very exciting. Let's just talk about this, this weird thing that's happening where we have a clock in a gravitational well. Suppose we have a rocket ship, okay? Now, a really, really, really tall rocket ship, okay? And this rocket ship has two people in it. We have Alice, and we have Bob. And Alice and Bob, I don't know how to draw the base of the rocket ship like that. Sure. Okay, so we have two people inside a rocket ship, Alice and Bob. Alice is at the very top of the rocket ship. Bob is at the very bottom of the rocket ship. And Alice is going to have something that shoots a little beam of light all the way down to Bob, and Bob is going to catch the beam of light and keep track of when it arrives. Okay? That is the main purpose of Alice and Bob inside this giant rocket ship. Okay, so suppose we make Bob's position ZB is equal to 1/2 GT squared, okay? Now that's gonna be Bob's position at any time. So we're just gonna say at any time, this is Bob's position, and G is the acceleration due to gravity, T is the time. Let's make this a function of T. Oh, and by the way, you don't have, if anybody is actually curious about this, you don't have to write it down. I've already done that, and I posted it on Discord. So if you would like to just read along, ! Discord, welcome to the Pony Crew. It's a good crew. ! Discord, and you can find any of these notes if you just want to follow along. You don't have to write anything down to get these. They're there already. So this is Bob's position. We'll say Bob. Now Alice is going to have a different position, right, obviously, because she's going to be at the top of the ship. So as a function of time, at any given time, she's going to be the height plus 1/2 GT squared, where this is really the same thing as Bob, and the only difference between the two is going to be some height h. Okay? Right? Good? So far, so good. Now, we have a couple things to consider about these pulses of light. So Alice is going to send 2 consecutive pulses of light down to Bob, okay? And let's get establish some variables. T is equal to 0 is going to be the first pulse. And we'll just say, for the sake of notation, I'll say that's emitted, and then this will be received, okay? The next one is T1. Now T1 is going to be the first, obviously, the first pulse received, okay? So this is going to be Alice, and this is going to be Bob. It's going to be emitted from Alice and then received. And it's just a pulse of light. Whatever that means to you, just a pulse of light. It could be a flashlight or... Oh, can you guys not see the board there? Oh, no, that's it. That's the arrows are where I end. Okay. I have to make sure I have a cutoff here, though. Okay. Now, then there's another time. So we'll call it delta tau A. And I'm just following the notation in Hartle, if anybody is interested. This is a general relativity book. So this is in there if you are interested. But this is the time that the second pulse is emitted. And the delta tau B is the second pulse received, okay? Oh, and I'm sorry, this is actually going to be, we want these to be, this is actually going to be T1 plus delta tau B, okay? That's the time the second pulse is received, okay? The distance traveled by the first pulse can be given by a simple formula. It's basically the distance from Alice to Bob. So these are just distances. Alice's distance minus Bob's distance. And that's going to be given by C times T1. Okay? And we know that, well, we'll get back to that in a second, but we can just talk about the distance as this, right? Okay. Now, the second pulse is going to be given by Alice's distance at time TB, or the distance of the second pulse, I should say, and then Bob's distance at the time T1 plus delta tau B. Okay. This is going to equal C times T1 plus delta tau beta minus delta tau a. Now, this is not to be too confused. This is just the speed of light, c. This is just a time. Namely, it's the time difference between when this was received and this one was emitted. And this is just the distance in space from when Bob received it minus the distance from when Alice shot it out. Now, this is going to be smaller than this. That's just kind of a given. Under the circumstance that this I should be very specific about this. There's one thing I kind of missed to mention. G is the acceleration, but it's not due to gravity. It's actually, we're going to say that this is in the middle of space, and this is the, hey sir, good to see you. And this G is actually the acceleration of the rocket, okay? So we don't want to use Earth's gravity yet, okay? Not yet. But we are going to say that it's actually the same gravity that we see on Earth, but it describes the acceleration of the rocket. Excuse me, that was a very important detail, okay? In space. Now, all right, let's get back. We got that cleared up. So now we have these two distances, the distance the light traveled in the first time, and it's not going to be exactly height because the rocket ship has traveled some distance, but you know, you get the point. Okay. Let's see. So let's plug in some of these things, okay? If we plug in the numbers from this down to here, we have this is a function of t, so we're just going to plug 0 in for that, and that gives us 0. Oh, this is for Bob. I'm sorry. That was the Alice one. So let's just do this exactly. So t is going to be 0, and then we get h minus, and then this is going to be t1, so that's just going to be 1/2 the acceleration of the rocket ship times t1 squared. And this is going to be equal to c times t1. Now, let's do the same thing for this one. Let's plug in these values up into our equation and see what we get. However, we're going to make one change, and that is that delta tau a, for the sake of simplicity, is very small. Okay, this was the approximation that I told Sarah we were going to make at the very beginning. This delta tau a is very, very tiny. That way, if we get any of these square terms, we can just ignore them because you're basically taking something really small, you're multiplying by itself, and making it really, really small. Okay? So we're going to ignore those terms for the sake of simplicity. Okay? So this ZA with delta TB is not going to really do too much because we want to ignore that. So we're really just going to get the H again. And then 1/2 GT1 squared from this term, right? And then we have one more term, which is G T1 delta tau beta. So we do have one, or tau b. We do have one of those terms that's linear and not squared. Okay, so I do have speech open for subs. If you are a sub and you would like to ask a question or anything about, or you cannot see something on the board or something like that, you can use !speak, and then say what's wrong, and then I will adjust it accordingly. Oh, don't just... Oh, yeah, we can plug this in. This is just the speed of light times the time difference, so it's good. Okay? Now, on the bottom we have, again, we just have the distances. And then, we just plugged everything in. Okay, now we're going to simplify this by subtracting these two equations. We're going to subtract this one from this one. That way this term goes away. So we're just subtracting equations. There's nothing wrong or inherently bad with that. It should be a good thing to do. Just an algebraic expression change. And we get the result. We're almost done. This is a very quick lesson. GT1 delta TB is equal to minus C delta tau B plus delta tau A. So let's simplify this. If we bring over delta tau B over to this side, we get delta tau B, and we can factor it out to get GT1 plus C. So we're bringing this term over here and just factoring out the delta tau B. And this is going to equal C delta tau A. Now, we're gonna do another little trick. Okay, well, let's plug in this. We already knew this from the get-go. T1 is equal to H over C. So we're gonna employ a scheme here where we multiply. Actually, let's write this term out just so we can see it out before we do the trick. And we get G H over C plus 1. Oh, C squared. Excuse me. Plus 1. is equal to dividing both sides by c squared is what we did here to get this c squared down here and this one to be 1, blah, blah, blah. Okay, and then, so now we get delta TB is equal to delta TA with this factor, and I kind of want to make this look a little cleaner. You can already kind of see what's happening here, but let's make it look a little bit cleaner by multiplying both sides by GH over c squared minus 1, okay? That gives us delta TB times g squared h squared over c to the 4th minus 1 squared, which is just 1, times delta tau a times the same thing, gh over c minus 1. Oh, c squared, excuse me. This term is not squared. This one is. You have c to the 4th, which is an incredibly small number. So we're going to just ixnay that for a second to see that delta tau b is equal to, and we're going to just move this minus over here, and we get delta tau a times 1 minus gh over c squared. And this is what we're doing right now. Now, you might think to yourself, okay, we have this nice little cute algebraic expression, but what does it mean? Did you miss some parentheses in the first equation on that board? Or have c in both terms? Yes, this is c. Did I screw that up? I might have screwed that up. Hold on. Let's, yes, I did screw that up. Very good catch. Very good catch. Yeah. We'll just put c on both of them. Okay. Excellent. And then here it's correct because we put the c back. So I just missed the c. Either the c or the parentheses. Either way, good catch. So this is it. So this is the time dilation. This is the difference. Let's remind ourselves what we found. Delta TB is the difference between when he receives the first pulse and the second pulse. Okay, so we got the first pulse at T1. He got the second pulse at T1 plus some difference in time, right? But this one is the time difference from when Alice sent the time pulse. What does that mean? It's weird, I know. But what that is saying is that under some circumstance of gravity, and I say gravity because I'm using acceleration, but really what we did with the law of, what's it called? Oh no, I forgot the most important law. This is like the most important law. The principle of equivalence, yes, because the principle of equivalence, there's like 4 of them. Yeah, but the principle of equivalence is what's telling us that gravity and acceleration of a rocket ship can act the same way, right? And in the gravitational well, depending on the height that the observer is, the 2 observers are apart, you actually get a difference in number, right? Now, of course, this changes dramatically once you want to include general relativity. Some of these subtleties are not necessarily the same, but in special relativity, we see here alone that the gravity and the height can make a difference, right? Murphy's law, isn't that? What's Murphy's law? I don't remember exactly. I want to say what comes up comes down or something like that. Anything that goes up, anything that will go wrong will go. Okay, yeah, okay. Cool. The screw up is relative. There it is. I see. I get it. Yeah, so this is the idea. So that's weird, right? We have a weird consequence of this. This is the weird consequence, right? My head ages faster than my feet do. Oh, let me just read it. Remember, I'm using a book. Okay, so these effects are extraordinarily small in ordinary laboratory circumstances. At the author's institution, the theorists that occupy the top floor of the physics building, the heart of the theorist is kind of a clock, right? As measured by a clock on the ground. A heart will beat more times on the top floor in a given interval of time than a heart of a similar physicist on the ground floor. And it will beat by a factor of 1 plus GH over C squared. So they're basically doing the opposite version of this by using this one. So this one will beat more times, making it a faster clock. And then, okay, that has recovered my my logic. But that's the big point of this, right? Is that time will go slower if you are at this point as opposed to some distance above the gravitational well, all showed by using the acceleration of the ship and the principle of equivalence to show that it can happen in a gravitational well. It's a nice result because it's so straightforward. It's very, very straightforward.